Is my screen visible?
Yes, sir.
Okay, so this is where we had stopped. Okay, so if I have a basis and this is a orthonormal basis set, then this scalar product of phi I and phi j will be the Kronecker delta function. Then any function f, any vector f can be expressed as a linear expansion of these basis elements, and these coefficients, this ai can be found in this way. Okay, these coefficients ai can be found in this way. You can work it out for yourself. Okay, how we can get this ai coefficients in this expression, you can just work it out for yourself. It's really straightforward. All you have to do is something like this, just expand this one. Okay, so this, so phi I, then f, so this is equal to phi I, then what is f? F is ai phi I. I'm going to use some other uh, index. I'll use j, aj phi j. Now by Einstein's summation convention, there is a summation which is implied here. So this means so this phi I, then this thing we have basically a summation over j, aj phi j. So now what you do is you expand this, so phi I, this one is a1 phi 1, a2 phi 2, and so on. And one of these will be ai phi I. So what will happen is, so we will have a1 phi I phi 1 plus, let's say, a2 phi I phi 2, and so on. And eventually we'll have something like an ai phi I phi I, and so on. What will happen is these will turn to be 0 because it's a orthonormal set. So only this one, this is going to be equal to 1 because of the Kronecker delta function. So what will be finally left behind is this phi I, the scalar product of phi I with f, that is going to give us, what is left behind is ai into 1. So this is how you get these coefficients. Okay, now in case this is not equal to 1, okay, in case this is not equal to 1, then sorry, in case it is not normalized, in case it's an orthogonal basis set but it's not normalized, then we can normalize this by modifying the coefficients. And we modify the coefficients in this way: we take the scalar product and we divide it by the norm of that same member of the vector of the basis. Okay, so that's how we do this. So let's do a problem so that we can understand this better. So the problem is, let me write this down. Consider the basis set. We'll consider a basis set, and that basis set will be chi n of x, and these are defined as sine of nx, sine of nx. Okay, so where n is equal to 1, 2, 3, 4, and so on. Okay, where for n equals 1, 2, and so on, in this will be the range 0, the range of values of x, 0 less than equals x less than equals pi. Okay, then here, of course, because if we want it to be a Hilbert space, then we need to define a scalar product, right? with a scalar product defined as, we define the scalar product in this way: some vector f and some vector g, their scalar product is equal to integration. The lower limit a, we'll set it to 0, and the upper limit b will set it to pi. Okay, 0 and pi. And then whatever is the function on the left side, we'll take the conjugate of that, then g of x, and the weight function, in this case the weight function is equal to 1 into dx. So that's how we define the scalar product. Okay, so now the question here is this: use these functions to expand this f of x equals x square times pi minus x. F of x equals x square into pi minus x. This is a cubic expression. This is a cubic function. Okay. So now first we check the orthogonality of the basis. Okay. So let's proceed then with the solution. First we check the orthogonality of the basis. And how do we check the orthogonality of the basis? Just take any two basis elements and then form their scalar product. Okay, so let us say I take this chi m, one with an index m, and I form a scalar product with another chi n. Okay, let's do this. Then what will this be equal to? What will this be equal to? We have to use this definition. We have to use this definition of the scalar product. That means you have to integrate from 0 to pi, a and b values 0 to pi. Then f star chi m star sine, what is chi m? Chi n of x is sine n of x. So chi m will be sine mx, and sine mx, it's a real function. So conjugate of that will be the same. Okay, so we will have here sine of mx, and then the other function g, this is the second function. The second function will be chi n, which will be sine of nx, sine of nx into dx. Okay, so let's call this equation number 1. Equation number 1. Now if m is to n, not equal to n, then chi m chi n, this will be obviously equal to 0 if m is not equal to n. Okay, so this is going to be 0. And how do we get that result? We get this result from your Fourier analysis. In Fourier analysis, you have this orthogonality of sine function. So from there, you'll get this. Okay, you can check for yourself. Okay, so this means that the basis is orthogonal. Okay, this means that the basis is orthogonal. Now let us say what will happen. Let's check what will happen if m is equal to n. Now if m is equal to n, then what do we have? Then the scalar product chi n, m is equal to n, chi n, this will be equal to, we'll have sine m and n are same, so we have sine square, so this is going to be equal to 0 to pi, and we have sine square and x into dx. Can someone evaluate this? All of you evaluate this and tell me what's the answer. Evaluate this. This is very straightforward. Anybody? What's the result? Yeah. Did you get the answer? Anyone?
Sir, half pi.
Yes, good. So it's going to be equal to pi by 2. I mean, that's very straightforward. All you have to do is you have to remember that the average of sine or cosine over, over any range is going to be equal to half. Sine square, sorry, not sine or cosine. The average of sine square or cosine square is going to be equal to half. So if I take average, right, how do you take average? So let's say if I take average of sine square, let's say I take average for over this length 0 till L. How do you take average of any function? You first integrate this function and you divide this over its range, so L minus 0, so divide by L. This will be equal to half, right? So you put L equal to pi. If I replace L and put a pi here, right, so you'll get, right, and this is going to give us, take the pi onto the other side like this, and this is going to give us pi by 2. Okay, so this is going to be equal to pi by 2. Okay, so let's give some numbers. This we'll call it as equation number 2. Equation number 2, that the fact that this is equal to 0, and this one we'll call it as equation number 3. Okay, so what does equation number 3, what does this imply? The when m and n are equal to m and n, when both are equal, then this is not equal to 1. If this would have been 1, then it would have been normalized. Okay, what is the meaning? How do you define orthonormal set? We define orthonormal set as this one, right? When you take the scalar product of any two members, it should be equal to a Kronecker delta. That means either 0 or 1. But here, when they're not equal, it is 0, that's fine. But when they're equal, it is not equal to 1. It is equal to pi by 2. So this tells us that this is not normalized. That is, sky n's are not normalized. Okay, so how do you obtain a normalized normalized basis set? That normalized basis set will be orthonormal. So therefore the corresponding orthonormal basis is, how do you get the orthonormal basis? We use this formula. We use the corresponding orthonormal basis. We use this formula. That these are the coefficients. Okay, these are the coefficients. So we have to divide this function. You see, we have to divide that basis function. We have to divide by under root. We have to divide by the norm. Okay, we have to divide by the norm. So that is going to be equal to phi n. Let's give it a new name. So from n, this is how we proceed. So we have here chi n. These are orthogonal, but these are not normalized. They are orthogonal, but they're not normalized. So we go from this chi n to another basis, which is phi n, and this phi n will be orthogonal and normalized. Okay, it will be orthogonal and it will be normalized. And the way we get this phi n, this is how we get this. Phi n is equal to, take this chi n, okay, the corresponding chi n, and that corresponding chi n you divide by under root, divide this by under root the self scalar product to the power 1 by 2. So that's how you do it. So this gives us the scalar product of chi n with chi n is equal to pi by 2. Okay, so you take this reciprocal of this and take the root over. So there's going to be a root over 2 by pi. So we'll get a root over 2 by pi. So this gives us phi n is equal to root over 2 by pi root over 2 by pi, and then the function, what's the function? The function is this one, sine, that is chi n, sine n x. So this is the function that we're looking for. Okay, so over here n will be equal to 1 as usual, 2, 3, and so on. Let's call this equation number 4. Okay, is that clear? So now we want to expand this. Okay, what's the question actually? Sorry, the question is we have to expand this function f of x equal to x square pi minus x. So we have to expand that function. So then to expand f of x, the corresponding coefficients, or rather instead of corresponding coefficient, let's say the necessary coefficients. The necessary coefficients are, that is, we want to know what is this an. Okay, we want to know what are these coefficients an, that we already know. The coefficients an, where is it? It's here. Yeah, the coefficients an are this. You have to take the scalar product of that corresponding phi, the normalized function, with the function f. Okay, so to find an, you have to do the scalar product of phi n, not chi, okay, normalized, phi n with the function f. So this is what you have to do. Okay, so this, let's go ahead and do this. So this is equal to scalar product. It's already defined. This is the scalar product. This is scalar product, integration from 0 to pi. So you have to integrate from 0 to pi. You have to integrate from 0 to pi, and then the first function is this one. The first function is this, Okay, that's the first function. No need to take the conjugate because it's a real function. And the second function is f, and which is a function f. The function f is x square into pi minus x. The function f is x square into pi minus x into dx. Okay, so and just get now this constant, and we will have this root over 2 by pi outside, and integration from 0 to pi, and what is left behind is x square into pi minus x into sine square, sorry, sine and x, not sine square, sine and x into dx, which can be evaluated now. Equation number 5. So you can evaluate equation number 5 and you can get this ans. Okay, so therefore I'll leave this to you. So therefore the expansion, the required expansion of this function f of x, and this function f of x is x square into pi minus x, and this expansion is, so basically ai into phi ai into phi I. So and these are your ai's. Okay, these are your ai's. So I could write this as a summation. So this is that constant which comes outside, and then we will have a summation over n, so n equals 1 to infinity because there is a summation, remember, and then we have sine and x, and then integration from 0 to pi, basically this expression 0 to pi x square pi minus x sine and x into dx. So this is a kind of expansion that we are talking about. So I leave this to you, work this out and then plug it in, and that is going to give us the expansion of this particular function. So this is what is meant by an orthonormal expansion. Is this clear to everyone? Okay, so scalar product expansion. So given an orthonormal basis set phi I which spans a vector space V. Okay, so if I have a vector space V, and this vector space V, it is spanned by an orthonormal basis phi I, then for any function, any two vectors f and g inside this vector space, we can write f as equal to some coefficient into these, and g we can write as some other coefficients into this. Okay, so we can write it like this. Then the scalar product of f with g is going to be equal to a star mu b mu, and the scalar product of g with f will be equal to a mu b star mu. Okay, so this I'll leave it to you, very straightforward. This in one step you can get this. And in the special case, if the function f, the vector f and vector g, if they are equal, then in that case, okay, both of them will be the same, f and f, or g and g. So this is going to be equal to a mu, okay, which of course it means this. This is what it means. This, because there is a repeated dummy index is repeated. So what this really means is you are taking the sum over mu. You are taking the sum over mu and summation over mu, a mu squared. So this is what it means. Okay. Okay, so now let's represent these as members as column vectors. But before that, let me do a problem, because that is going to another problem. Just a minute. Yeah, let's do a problem a little bit later. First, I'd like to show the column vector representation. Okay, so now you see here. So we have we can write the function as a linear combination of the bases, and the basis is known. So all that you need to worry about are the coefficients. For the function f, we need to worry about these coefficients. For the function g, we need to worry about these coefficients. Okay, so now why not take all of these a coefficients and b coefficients and write them as a column vector like this? So we write this a coefficient. So this function f, we write it as a mu phi mu. Okay, this is already known to us. This is already known to us. So take this a mu coefficients and you write this as a column vector. Okay, so similarly, do the same thing for this b vector. Okay, then this scalar product. Okay, the scalar product of f with g. So remember here, f is equal to a mu phi mu, and g is equal to b mu phi mu. So if I take the scalar product f with g, so what are you essentially doing? You have to take the conjugate of this. So taking the scalar product is equivalent to, so earlier this a coefficients, this was giving me a column vector. Similarly, this b coefficients, it was giving me another column vector. But the moment, whichever is a column vector, if it goes to the, if it becomes the first function, if it represents the first function, then this column vector will become a row vector. Okay, so this column vector is going to become a row vector, and because it happens to be the first function in the scalar product, so we'll have to put a conjugation also. A conjugation also has to be put in. So that's why this a1, a2, and so on, it from a column vector it becomes a row vector, and this a1, a2, and all of them, they became conjugates. So that's how we get this. So now this is very straightforward, because what is this? Suppose there are n elements, so this is a 1 cross n matrix, right? And this one, number of rows is 1, number of columns are n. Here number of rows is n, and the number of columns, only one column is there. So when I multiply this, these two should be equal. So what is left behind this? 1 cross 1. So what we should get here, the result of this should be 1 cross 1. That means we should get a number. And what will that number be? A1 star into B1. Okay, so we'll get A1 star into B1. Then we'll get A2 star into B2, and so on. AN star into Bn. So which of course we can write it as, A mu star into B mu. You could write it like this also. Okay. And in terms of the matrix, in terms of the column vector, this simply is written as a dagger. I hope you remember what is this dagger symbol. What does this mean? This dagger symbol, what does this mean? Implies, what does it imply? Conjugation and transposition. Do you remember the dagger symbol? This dagger symbol. What does this mean? It means conjugation and transposition. So suppose I have something like this. I have, let's say, a matrix. Okay. Let's say I have a matrix. Okay, this is the matrix. So this matrix is, let's say, I3 minus 2I plus, not plus, 7. Okay, so suppose this is the matrix. Then what will be this A dagger? A is this one. Then what will be A dagger matrix? Can anyone tell me? What will be A dagger? A dagger means conjugation and transposition. So first let us transpose this transpose this matrix. The rows will become columns, columns will become rows. So first row will become the first column. First row is 1, 3. So that will become the first column. 1, 3. Second row minus 2, I, 7. So minus 2, I, and 7. So this is going to be, this will be the transposition. Now what you have to do, you also have to do conjugation. So conjugation means I is going to become minus I, and minus 2I is going to become plus 2I. So this is what this is the meaning. Okay, so if I have a column matrix, the transposition is going to give us a row matrix, and the conjugation is going to give us these little stars on each of these coefficients. So, and this we can represent as A dagger. So this entire matrix, this is your A dagger matrix, and this is your matrix B. Okay, or vector A dagger and vector B. Just do this multiplication, you will get the scalar product. Is this clear? Is this clear to everyone?
Yes, sir.
Okay. Okay, so then further, if G is the same as F, then it will simply become A dagger B. Instead of A dagger B, it will become A dagger A. So self scalar product is also in terms of the coefficient vector. So it will simply be equal to A dagger A. Then we have something called as a Gram-Schmidt orthogonalization process. So I'll do it in the next class. So now I'm going to stop with an example problem, okay, which I told you. Okay, let's do that problem just to illustrate whatever we have learned over here. The problem is this. A set of functions that is orthonormal on this particular range zero less than equals x less than equals pi is given as, let me write down this basis function that we're talking about over here, that is phi n of x is equal to under root two minus delta n 0 divided by pi cos nx for n equals 0, 1, 2, and so on. So here we will need to expand a function, two functions actually. Two functions. So first function I'll give here, the second function. The first function is f of x is equal to cos cube of x cos cube of x plus sine square of x plus cos cube of x sine square of x plus cos x plus 1. And the second function is g of x. It is defined as cos square x minus cos x, okay, in terms of these phi n's. All right, and then we'll have to obtain, once we do get this, then we'll have to obtain these scalar products, that is scalar product of f and g, the self scalar product of f and the self scalar product of g. Okay, so these are things that we have to do over here. So how do we go about and proceed with this? So this is again 0 1 2 3. Okay, so we can use this column vector approach here. Okay, so to solve this, we have this, let's write down this. So we have phi n is equal to, as given, the phi n of x is equal to 2 minus delta n0. What is this? This is the Kronecker delta function, right? It will be 1. This will be equal to 1 when n is equal to 0. For all other values of n, this will be equal to 0 only. Okay, divided by pi, the whole thing under the root cos of nx, cos of nx. So therefore, let's just write down a first phi naught of x. What will be phi naught of x? Let me grab this so that I can just reuse this. Okay, so we have phi n, right? So we have 0 here. So this is going to become delta 0 0, and then there is a 0 here. So this will become cos 0. So what will this be equal to? This will be equal to, inside here, so we will have under root, so we have a 2 minus delta 0 0. You see, both of these indices are the same. If both indices are same, according to the Kronecker delta function, it should be equal to 1 divided by pi, and cos of 0 is of course 1. Cos of 0 is 1. Then what is left? 2 minus 1 is 1. So this gives us, this is equal to 1 divided by root over pi. So this is your phi 0. So likewise, what about phi 1? Phi 1, what will this be equal to? Let me just grab all of these. Phi 1, what will happen is, again, this instead of 0, this will be equal to 1. This will be 1 0, and this will be cos nx, so cos x, and here we will get delta 1 0, Kronecker delta function, delta 1 0. This will be, because the indices are not the same, so this will be 0 here, and we will get a cos x, which will remain the same, cos x. So this is going to give us root over 2 by pi into cos x. root over 2 by pi times cos of x. Okay, so in a similar way we can find out phi 2, okay, in a similar way, okay, in a similar way, phi 2, and what will phi 2 be equal to? It will be equal to root over 2 by pi into cos twice x. This will be root over 2 by pi into cos of twice x, and phi 3 in a similar way, phi 3 will be equal to, instead of 2 we'll have 3x cos 3x, and so on. Okay, is this clear to everyone how I got this? Is everybody clear with this?
Yes, sir.
Yes, sir.
Okay, so now let's go to the function. The function is f of x equal to cos cube x plus sin square x plus cos x plus 1. So now this function f of x, we'll just write down, we'll use our trigonometric identities. So this function f of x is equal to cos cube x plus sin square x plus cos of x plus 1. So this one, cos cube x, we can use the trigonometric identity, that is cos thrice x plus 3 cos x, cos thrice x plus 3 cos x divided by 4. What about sin square x? Which identity can I use? Sin square x. You can use 1 minus cos of twice x. 1 minus cos of twice x divided by 2. Then cos x, will leave it as it is, and 1. Now can you see the reason why we are writing it like this? Because we have a cos thrice x, so cos thrice x we can write it in terms of phi 3. Then there is a cos 2x we can get in your phi 2, and cos x we can get phi 1, right? And this is a constant, 1 is a constant, we can get it phi 0. So with a little bit of manipulation we can actually go ahead and we can do that. So let's open up these brackets. So we first have 1 by 4, so we have 1 by 4 cos 3x, 1 by 4 cos 3x. Then we have 3 by 4 cos x plus cos x, 3 by 4 cos x plus cos x, that is going to give us 7 by 4. 7 by 4 cos of x. Then here we'll get a minus half cos 2x. And did we miss anything? This is done, this is done, this is done. Okay, then we have 1 by 2 plus 1. 1 by 2 plus 1, that is going to give us 3 by 2. Okay, so that is 3 by 2. Is that clear? So from here, this implies that 1 is equal to root over pi into pi naught. 1 is equal to root over pi into pi naught. This implies that cos of x is equal to root over pi by 2, root over pi by 2 into pi 1. Same thing for the others as well. Cos twice x, cos thrice x also. We'll get a phi 2 here. So cos twice x will be equal to root over 2 by pi into phi 2. And likewise over here, so cos 3x is equal to root over pi by 2 pi 3. Okay, so this is what we have. So now we'll make this substitution. Cos 3x will replace with this, cos 2x will replace with this, cos x will replace with this, and wherever there is 1 we'll replace it with this. So we have here, so this will be equal to, this is equal to, let me just grab this whole thing. So 1 by 4. So cos 3x, okay, cos 3x, which is cos 3x, cos 3x is this one, cos 3x is this one, okay. So we bring in, instead of cos 3x, get rid of this and we replace it over here. Then we have cos of twice x, so minus half cos of twice x. Cos of twice x is this. In terms of phi 2, let's bring it here, get rid of this cos of twice x and put in phi 2 over here. Then cos of x is this one. So cos of x, and then we have finally 3 by 2, 3 by 2 times 1, 3 by 2 times 1, so we might as well just get this one, root over pi into phi naught times root over pi into phi naught. Is this clear? So this gives us f of x to be equal to, let's simplify this. I could take this root over pi by 2, this root pi by 2, I could take it outside, common, take it outside, and what is left behind would be we have phi 3 by 4, phi 3 by 4, then we have phi 2 by 2 minus phi 2 divided by 2, then we have 7 phi 1 by 4 plus 7 phi 1 divided by 4 plus because we have taken root over pi by 2, so there's going to be root 2 extra over here, so you'll get 3 root 2 by 2, 3 root 2 divided by 2 into phi naught. This is what will be left behind. Okay, is this clear, everyone?
Yes, sir.
So now this other one, the g of x, I'm leaving it to you. Please do it now. G of x is cos square x minus cos x. G of x is equal to cos square x minus cos x. So I want you all to follow the steps that I have done here and do it right now. Please do this. 2 minutes. Please do this. This is easy, okay? I'll help you. So this is going to be equal to, cos square of x. Cos square of x can be written as cos twice x plus 1 divided by 2. Cos twice x, plus 1 divided by 2. So this is your cos square of x minus cos of x. Please proceed in this way. These I hope you have noted down. Only thing is the 1 is equal to root over root pi into phi naught. Rest cos 2x, cos x, cos twice x, cos thrice x. We have these. Please write this down in terms of phi 1, phi 2, phi 0, phi 1, phi 2, phi 3. Please write this down. Take out your notebook and do it now. Phi 3 will not appear in this expression. Phi 3 will not appear because only cos is there, cos x is there, cos twice x is there, and 1 is there. So only phi 0, phi 1, and phi 2 will appear. There will be no phi 3 here. I think it will be better if I leave this to you to try at home. I'll give you the answer here. So this will be equal to, g of x will be equal to the steps in between. I'll just leave it to you, okay? Okay, the steps in between, please fill these up. And what you will get here is root over pi by 2 root over pi by 2 and what is left inside the brackets will be phi 2 divided by 2 minus phi 1 plus root over 2 phi naught divided by 2. So this is what is going to be left behind. Okay, please try this out at home. Okay, let's just proceed from here. Okay, so we have f, we got this, and this is g. Implies g of x is equal to this. So f of x is this and g of x is this. So once we have this f of x and g of x, so we can write down the coefficient matrix. Okay, we can write down the coefficient matrix. So therefore the coefficient vector, the coefficient vector for f of x is, let's call this as a, let's call this as small a. This will be equal to root over pi by 2, root over pi by 2, and then these vector elements. Okay, so what are you multiplying with phi naught? First we'll have the coefficient of phi naught. Coefficient of phi naught is root 3 by 2 in root 3 root 2 by 2. Okay, so first will be 3 root 2 by 2. First we'll have 3 root 2 by 2. Then next, whatever is the coefficient of phi 1, which is 7 by 4. 7 by 4. I think it's better if I write it in a different way. The first one will be 3 root 2 by 2. Next one, coefficient of phi 1 is 7 by 4. Collect all the coefficients, 7 by 4. Next one will be coefficient of phi 2 is minus half. So collect minus 1 by 2. Okay, and the last one will be 1 by 4. So take this 1 by 4. So we get this will be the coefficient vector. Okay, the coefficient vector of f of x is this. In a similar way, therefore, the coefficient vector of g of x, what is this? Let's call this coefficient vector as b. This will also have a root over pi by 2. Can anyone tell me what will be the elements?
Root 2 by 2.
Good. So first we'll have root over 2 by 2. Root 2 by 2. Then next one will be
Minus 1. Minus 1.
minus 1. Next
Half.
1 by 2. And the last one
0.
0. There is no coefficient of phi 3. If there is no coefficient of phi 3, then just put a 0 there. All right. So put the brackets here. So these are your vectors. Okay, the coefficient vectors. So we have coefficient vector of f and the coefficient vector of g. Now it is very easy. Now it is very easy because we need to find out what is these. What are these scalar products? Okay, we need to find out what are these scalar products. F, G, F, F, and G, G. Okay, so therefore, first F and G. What will this be equal to? It is equal to FG. It is A dagger B. It is A dagger B. Okay, so A dagger B. A dagger B. A dagger B means you have to transpose and then you have to conjugate. Dagger means transposition and conjugation. Here no need to take conjugation because all are real numbers. So only you have to take transpose. Now this root pi by 2 and root pi by 2 will get multiplied and we'll get root pi by 2, root pi by 2. We will get pi by 2. The root over will go and then we'll get pi by 2. Okay, we have pi by 2 and then this one from a column matrix is going to become a row matrix. So we will have here, this is going to be 3 root 2 by 2, first element. Next element is 7 by 4. Next element is minus 1 by 2 and the last one is 1 by 4. Okay, so these are the elements. Let's close the bracket. Then this one. Okay, tell me the result. Multiply these two and tell me what the result is going to be. Did anybody get the answer?
So minus pi by 4.
Very good. It should be minus
Minus pi by 4.
pi by 4. Good. In a similar way, you can do for the self scalar product. That is f similar way. Okay. So this will be simply a dagger a. Okay. In a similar way, please work this out. I'll give you the answer. This should be 63 pi by 16. That should be the answer. Please work this out. Okay. And finally, G self scalar product G. This will be equal to B dagger B. Likewise, please work out this also at home. And this answer should be 7 pi by 8. Okay. Is that understood by everyone?
Yes, sir.
Has everybody understood this?
Yes, sir.
Yes, sir.
Yes,
Right.
sir.
Next, we have a very important tool which is called as the Gram-Schmidt orthogonalization process. What happens in Gram-Schmidt is if I have a set of functions which is neither orthogonal nor normalized, okay, it's not that it always has to be orthogonal. No, if we have a set of functions where if and these functions are neither orthogonal nor normalized, you can actually use this set of functions to construct an orthonormal set. Okay, so suppose let's say I have a 5-dimensional vector space. 5-dimensional vector space means you take any basis, it will have 5 members, or it can be comprised as a linearly independent. So any vector can be written as a linear combination of 5 different functions. So that is the meaning of a 5-dimensional vector space. So suppose I have a vector space, 5-dimensional vector space. It is not that you have to always have orthogonal functions using that with which you can get a basis. No, I can take any 5 functions, and these 5 functions need not be orthogonal. Okay, so take any 5 functions, and from these 5 functions you construct an orthogonal a set which is orthogonal as well as normalized. So this process is known as a Gram-Schmidt orthogonalization process. It is a little bit involved. It's already 2:30, so I'm going to stop over here and I'm going to continue from this in the next class. Okay, any questions? Does anybody have any questions? Okay, if